to the ones tomorrow. Excuse me. Tomorrow, 11 to 12 and 4 to 5. All right? Right. Yesterday I talked about inference for population mean, right? And today I'm going to talk about inference for population variance, right? So suppose you have a random sample from a normal distribution with these parameters, right? And what we like to test for is the population variance, or the same as the population sigma. Remember, sigma denotes the population standard deviation. Sigma squared denotes the population variance. So they are both equivalent. Okay. So you can test this, or so once again, there are three possible tests. There are three possible tests for the population variance or the population standard deviation. This, or this. Let me put a line here, and a line here, and a line here, and a line here. Okay, guys. Now, for the first test, you will reject the null hypothesis if right, this is the rule for rejecting the null hypothesis for this test. And the second test, this is the rule for rejecting H0 for the second test. For the third test, this is the rule. Now, once again, guys, now, as I said to you yesterday in the lectures, these rejections rules, they came from using the Neyman-Pearson lemma, right? In other words, all these, if I have a red pen, let me see one, not this one. All right, here we are. So these these rejection rules were obtained by by applying the Neiman-Pearson lemma, which I talked about a week or so ago, guys. You may recall. So hence, come on, guys. All these pens stop writing. I don't know why. Hence, the tests are most powerful. Remember the word most powerful, what it means. What it means is that if you draw the power function corresponding to these three rules, right? If you draw the power function for each of these rules, you cannot have another power function that is better than the power functions for these, right? That's what the term most powerful means that, okay? All right, guys? All right, let me put it here. Now let me label this test, guys, because I've used, let me call this 7, because I already call this 8, call this 9. Because I have already made 1 to 6 yesterday, all right? So let me call this test 7, 8, and 9, okay? Now, what I'm going to do, guys, now is to, because I don't have the time to do all three, I'll just do one of them, okay? So what I'm going to do is, I'm going to show you how to derive the power function for test number 7, okay? All right, now, so you start with pi of sigma. Remember, this is the notation for the power function, which is defined as the probability of rejecting H0 given the value for sigma, right? So this is the probability that yeah. So this is equal to this, right? Now, because these two events are mutually exclusive, that means they cannot occur together, we can write this as the sum of the probabilities. So this will be all right? You see what I've done? Because the two events are mutually exclusive, you can write this as the sum of the two probabilities. All right, the next thing I'm going to do is we are conditioning on the fact that the true population standard deviation is sigma. The same thing here, right? Now, what you are dividing by here is sigma 0 squared, which is not the true, population variance. So the next thing you must do is to change this guy here and this guy here to the true population variance. So I'm going to change this to sigma squared, and therefore I need to multiply by sigma squared, right? And the same thing here, guys. I'm gonna change this to sigma squared. Therefore, I need to multiply by sigma squared. Right? So you see what I've done, guys. The reason I have done that is because we are conditioning here, we are conditioning on the true population standard deviation being equal to sigma. So the true population variance is equal to sigma squared, right? So you must have that here and here, okay? So the next thing I'm going to do, guys, is to take this to the right-hand side and take this to the right-hand side, all right? So it becomes it becomes this. Yeah. All right. Now, if you look at these guys, this one and this one, I think you know the answer to my question, I guess. What distribution will this have, guys, and why? Yeah. This will have chi-square distribution, right? It will have the chi-square distribution with n minus 1 degree of freedom. Okay, we don't need the conditioning anymore because we have used the conditioning to argue that this has a chi-square distribution. So the conditioning is no longer needed, all right? Right? That's it, guys. So I have used, in this step, this is a crucial step where I have used, if you look at the lecture note, guys, I have used equation 72 in the lecture notes to argue that these two guys have the chi-square distribution, right? So the power function of sigma is equal to the sum of these two probabilities. Right, and if you have a I mean, I know some calculators can draw this. If you can draw a graph of this, you will see a shape that will be the most powerful shape. In other words, the power function that you will get by drawing this will be the closest you can have to the ideal power function, right? Okay. I'll let you do that when you have time, guys. Right. Okay. Now the next topic, guys. So I've only done this power function is only for 7. It's for test number 7, guys. Now I know there is also test 8. There is also test 9. Now when you guys have time, please. I'm not going to do them today because I don't have time, but when you guys have time, try to also derive the power functions for test 8 and test 9. Okay. So maybe I will write this down. Homework. Right. Okay. So do that when you have time, guys. Okay. All right. All right. Here we go. Next one. The next one is one sample test for population proportion, right? Right. So you have here, guys. You have a random sample from a Bernoulli distribution. You guys remember the Bernoulli distribution? This is the first thing we talked about in this course. You guys remember? I think I talked about this in the first lecture of this course. What is a Bernoulli distribution, guys? It's a Bernoulli random variable takes only two possible values, either 0 or 1. Right? 1 with probability p, 0 with probability 1 minus p. So for example, like in practice, it could refer to whether you smoke or not smoke, whether you have a car or don't have a car, whether you pass or fail. So things like that can be described by Bernoulli, right? Where you have only two possible outcomes, guys. Yeah? Okay. Now in this case, P represents the proportion of ones. So, for example, P could be the proportion of people who smoke, or the proportion of students who passed the test, or the proportion of people who have a car, or something like that, right? So P is the proportion of successes, right? So in this case, once again, there are three possible tests, right? So yeah. All right. So these are the three possible. Let me draw. So these are the three possible tests. For the first test, we right? You reject that hypothesis if this is the case. For the second test, all right, so these are the three tests, guys. Now, there's some, I mean, unlike the two previous cases, remember yesterday we talked about tests for population mean. And so far today we had talked about tests for population variance. And all those tests we talked about so far are most powerful tests. In other words, they were obtained using the Neyman-Pearson-Lamar. But unfortunately, these three tests, let me call them names, okay? Let me call this as 10, right? 10, 11, 12, right? I'm just numbering them from 1 to, because we had 7, 8, 9, so it's 10, 11, 12, all right? Now, these tests are not most powerful, and the reason is the following, right? These tests are not most powerful. The reason that they are not most powerful is because the reason that they are not most powerful is because these tests assume that x bar is a sample mean, has an approximate normal distribution, which is not which is not an exact result, because when you have a random sample from a Bernoulli distribution, x bar is not normally distributed, right? But when you these three rules for rejection, they assume that x bar has an approximate normal distribution, right? So under that approximate assumption, these rules are derived, and hence they are not most powerful, right? They assume that the x bar has an approximate. So that the approximation, when you make an approximation, the result that you derive is no longer an exact result. It's only an approximation, right? So hence, the test that you get cannot be the most powerful test, right? Okay. Is that clear, guys, or not? Right. Anyway, once again, let me. Although these tests are not most powerful, let me show you how to derive the power function. Right. So I'm gonna. I'm going to show you guys how to derive the power function of test number 10. And I will only do 10, and 11 and 12, please, when you have time, try to do the same for test 11 and test 12, okay? So I'm going to start with pi of p. P is the parameter of interest, right? Is by definition is the probability of rejecting H0 given the value for p. Okay, and this is right. This is the rule for rejecting, the one here. Okay. Right now, guys, I think I told you this yesterday also. When you have an absolute sign, guys, you have an absolute sign here, right? You must always get rid of it, right? How to get rid of an absolute sign? You do the following, guys. You say, right? You say that it's either greater than z alpha by 2 or less than that. Yeah. Remember, like, I think you know this, guys, from your if you don't know this, I will write it down. If you have something like this, the absolute value of z is greater than a, then that's the same as saying that I'm sure you know this result, right? This is the same as this event, right? Right, the next step, I'm going to, because the two events are mutually exclusive, we can write the probability as a sum of two probabilities. Right, so this will be all right. So this is using mutual exclusive, mutual exclusiveness. All right. The next thing I'm going to do is, remember, we are conditioning on the fact that the true population proportion is equal to p, and what you have here is p0, right? So what you must do is to replace p0 by p, right? So the same old trick again, guys. So you get so I'm gonna replace p0 by p, and therefore I need to add a p and keep this. You guys are you guys with me or no? Yeah. All right. Now the next thing to do is to group these variables, group these two, and take them to the right hand side. Take them to the right hand side. Okay. So let me put this over here, guys. So I'm running out of space here. All right. So the next step is to right. Yeah. And I know it's kind of boring, but just bear with me, guys. Yeah. So you see what I've done? I have taken this guy to the right hand side and this to the right hand side too, right? Now, okay, this is where the trick comes in, all right? If you look at this one here and this one here, I'm going to make the following. I'm going to assume, let me put it in red. I'm going to assume that X bar has a normal distribution, although this is going to be approximate one. So when I put a dot behind this, I don't know whether you've seen this notation before. What this means is that we are saying that X bar has an approximate normal distribution, right? I'm going to assume that X bar has an approximate normal distribution with mean equal to P and variance equal to this. This means right. The notation means approximately distributed as normal distribution. All right. So I'm going to put this in a box, guys. Right. Now, under this as approximate assumption, right, this guy will have what distribution? Standard normal, okay? So that becomes, so this is once again a notation for approximate. So this will become the N01 greater than and the second one will become all right, guys. All right, and the conditioning on P is no longer needed because I have used the conditioning to argue that this and this have the standard normal distribution. So we don't need the conditioning anymore, okay? So finally, this becomes 1 minus phi yeah, and phi Right, so this is the power function for test number 10. This is test number 10, guys. Okay. Now, what I like to tell you guys is that this power function is not most powerful, because the reason that this is not most powerful is because of the assumption that we made here. This assumption here is not an exact result; it's an approximate result, right? And that is precisely why. That's precisely why this. That's is not. That's precisely why that this power function is not a most powerful function, right? All right. Okay. All right, guys. Next one, we are turning to page 24. Do you have the notes with you? Right. Sorry, guys. Inference for equality of means. Now, X, guys. All right, so here we have, so far we talked about one sample inference, right? So starting now, we're going to talk about two sample inference, where you have two different samples. Like here, for example, we have a sample x1 to xm from a normal distribution with these parameters, and another sample y1 to yn from another normal distribution, and the two samples are independent of each other. And what we want to test here is, all right, and also, okay, just a minute. Assume all right, what we want to test here is whether the means of the two samples, the means of the populations where the samples come from are equal or not equal, right? So there are, once again, there are three possible hypotheses, right? The first hypothesis is that is this one. So here we are testing whether the means of the two populations are equal versus being not equal. Okay. And the second one is this, and the third one is all right. So these are the three different tests. Let me put some lines across. All right. For the first test, we reject H0 if all right, this is the rule for rejecting the null hypothesis for the first test. And for the second one, we reject H0 right? And for the third one, all right? So these are the three different tests. Now, these tests, I must tell you this, these tests were derived using the Neyman-Pearson lemma. Hence, they are most powerful. So these tests are indeed. So you should draw the power functions for the three tests, for these three tests. That's the most powerful power function you can have, right? In other words, you cannot have another power function that is better than the power function of these tests. So for the sake of numbering, let me call this 13, 14, 15. I'm just numbering all the tests, okay? Now let me show you guys let me show you how to. I'm gonna do only one of these, right? And the remaining two you have to, please, when you have time, do it by yourself, guys, okay? If you have problems, come and see me or send me an email, right? Okay. Okay, I'm gonna show you how to derive the power function for test number 13, right? Now, in this case, In this case, the power function has two arguments because we are concerned about two parameters, right, mu x and mu y. So it's a function of two parameters, right? So this is so it's a probability of rejecting H0 given the parameters mu x and mu y, right? So this would be the probability that right? The first thing, I know we have done this enough times, so the first thing you must do is to get rid of the absolute sign, right? And how you do that? You all right, you see what I've done, all right? Because when you get rid of the absolute sign, you get two possible, either this happening or this happening, and these two events are mutually exclusive. Hence, you can write them as the sum of two probabilities. Sorry guys, I know I'm running out of time, but sorry, what's this? All right. The next thing to do is to look at the distribution of x bar, y bar, and this is why I need to refresh your memory of the stuff we did in week 1 and 2. I know you've been having a lot of midterms, guys. I think you should spend more time in my course because you had all your midterms so far by now, right? I'm not just kidding, guys. Right. You know that, from, if you remember, if you go back to week 1 and 2, what we did, do you guys remember the distribution of x bar? X bar has what? Normal distribution with parameters. Yeah? And do you guys remember y bar similarly will have? Right. Now, so now the x's and the y's are independent of each other. So what if this is x bar has this and y bar has this, what distribution x bar minus y bar will have? We'll also have a normal distribution with parameters. Do you guys remember this? I think this is stuff we did way back, long time ago. Right? Do you guys remember this stuff or not? So now, although I'm run out of time now, you need to use this result to simplify this, right? Can you try to do that by yourself, please? Because I don't think I have the time now to finish. Yeah? Use this result here, this one. Try to simplify these probabilities, right, by yourself. If you can't do it, I will do it next time I meet you guys on Tuesday next week. But hopefully you can do this by yourself. All right. You're right. Good. Yeah, how are you?
That's the random variable. It's also in this distribution.
Which one?
That's that.
Yeah, I know, but this is an approximation, I told you. It's an approximation. It's not an exact result. This is...
X bar is a random variable.
Yeah, I know.
Random variable in a distribution.
You can have... Yeah, I know, it doesn't make sense, but it's kind of an approximation.
Yeah, but we can change it to P.
Yeah, but you need to have X bar in order to use this result. I know X bar is a random variable, but you shouldn't have it here. But it's kind of it's like a loose argument. I know it's like a loose argument. You shouldn't have X bar for the variance. Yeah, but I think in order to use it here, you need to have an X bar here. Otherwise, you can't simplify this.
We can change it to P.
Yeah, you can have it P. Yeah, but for practical use, you don't know the value for P. Like when you have a data, you don't know what P is. That's why they put it as X.
But that's a function of P. But that's a function of P.
It's a function of P. Yeah.
Yeah, you can give P a value and you can get
Yeah, maybe. Yeah, you can do it that way too. Yeah, you're right. But this is the way they do it in books, though. If you look at books, they use X bar, not P. They use X bar.
If you use this, it's now normal distribution.
Yeah. Sorry?
It's now normal distribution because this is, you think it's a random variable.
Yeah, it's a random variable, but I mean, for the purpose of the variance, we are assuming that X bar is fixed. It's a fixed number, not a variable.
It's a fixed number, how can it be a random variable?
Yeah, it is. It's still. I know it's confusing. But this is how they do it. You know, if you look at books, you will see this. This is how they do it.
What kind of books?
I will tell you maybe tomorrow when I see you. I can't remember the books, but they normally approximate P by X bar. That's how you get this. Yeah. You have the same question or what? Yeah. What?
How do you know these two events are destroyed?
Because one is greater, one is less than. So they are one is greater, one is less. So they must be mutually exclusive.
You mean destroyed?
Disjoint, yeah.
But I draw this picture. If alpha is big, is too big.
No, alpha is usually small. It's like 5%. So alpha is usually like 0.05. Yeah, it's 0.05. So in that case, this will be this point here, and this will be this point.
Bigger.
Yeah, this is bigger. Yeah, this is bigger than this.
Because alpha is small.
Small, yeah. Usually alpha, people take alpha to be 0.05, 0.05. Yeah. Yeah, that's why this is bigger than this.
So we always assume alpha is that within that range.
Yeah.
So these two events are destroyed.
Yeah, exactly. Yeah.
Thank you.
All right, thank you. How are you, madam? You okay?
Yeah, but don't say question. Yeah, it should. We should use the hypothesize the population proportion.
Yeah, it should be P instead of X bar. Is that what you're saying? Yeah. The reason is X bar is because if you put P here, you cannot simplify this. You cannot simplify this if it is P.
Why not? We cannot simplify.
You have the same question? Or not? Because remember, I know the X bar shouldn't be